Linear functions are used very often because they're so simple and easy to work with, even though things could get a little bit too simplified sometimes. Sometimes it's perfectly okay. So we're looking at 1.4. This is now the updated version, so make sure sometimes you have to refresh. If you, even if you go to the website, you click on the problem book, it might have it in the memory and just bring up an old version, so make sure you have that as the first question. We'll just do the first few. Number 1, taxi service. I don't have it here. The taxi service charges 50 cents per mile plus a $5 flat fee. What would be the cost of traveling 20 miles? What would be the cost of traveling X miles? So they're really asking me, what is the cost function? So we're doing 1.4, number 1. So they've defined the variable for me. I can remind myself that X is the number. I realize I need to switch the screen. I'll switch back and forth as we need. You should have the problem book in front of you anyway. Number of miles. And I can remind myself I have 50 cents per mile and a $5 flat fee. So I need to define a letter. I don't want to use Y always. Let's go C for cost. Let's go C represents the total cost. So I want to find the cost function. But I realize that this is already a change in cost per change in X, because it's per mile. So for every 1 mile, I'm charged 50 cents. So that means that this is the slope M. So my cost function so far is C, not Y. It's really 50 cents over 1 times X plus B. Because of how they give me that cost per mile. That is the change in the cost for 1 extra mile. And this flat fee is how much I would travel, or how much I would pay if X is 0, which means it's the Y-intercept, which means it's the B right away. So they were very kind to give me all the things I need for my slope-intercept form right away. Didn't have to do much, but in some cases, of course, not that simple. It's our first example. So don't always expect the worst. Sometimes it's very nice in how they give me the information. And it's as straightforward as just realizing that those numbers are exactly the numbers in my function. Let's look at number 2. Is that big enough to read? You should have it in front of you anyway. I should actually make it smaller so that you're encouraged to go get the problem book yourself. Can you read that? Now? Can you read it now? What about now? Now? Number 2. It costs $750 to manufacture 25 items and $1,000 to manufacture 50 items. Assuming a linear relationship holds, find the cost equation and use this function to predict the cost of 100 items. I realized that in the previous one we didn't find the cost of traveling 20 miles, but you just plug in 24x and find the number. We'll skip that. You can do that yourself. So for this one, the information is a little different, but we are still looking for a straight line equation or a linear function. This will be number 2. So I have $750 that goes with 25 items. I have $1,000 and that goes with 50 items. And then they say my cost function is what I'm looking for. And once I have that, I can answer everything. And they say it's linear. So I want to use a y equals mx plus b form because I don't need any other form. That's more than sufficient. But what is the very first thing that I need to do for a word problem? It was yesterday, around 24 hours ago. First step, there's always 4 steps. If they don't do it for me, like the previous question did, so I could get around that. First step is I need to say what is x if I want to use an x, and what is y if I want to use a y, before I can actually use it. Let's say x represents the number of items, and let's go y. But you can be a little bit more creative. It could be anything you want. The cost, the total cost. Then I can say, because they are assuming a linear relationship, I'm looking for y equals mx plus b. I don't have to define the m and the b. That's the standard letters we use for the slope-intercept form. Now, which one do you want to find first, the m or the b? They don't give me b directly, which means it's probably going to have to wait. M. Now I know the m is the change in y over change in x. Really, if you have different names for your variables, it's really the change in the output variable over the change in the input variable. So just be careful if your names are different. You don't have that familiar x and y that you can rely on. So that's going to be, we can take this as the first situation, this as the second. It's going to be 50 minus 25 over 1,000 minus 750. How do you feel about that? I didn't say it was right. I just checking how you feel about that. He doesn't like it. Does anyone support him? You have one supporter. Better than nothing. What is not right there?
He said y was going to be the cost.
Yeah, see, once we define our variables, we have to stick with this. And if y is the cost, then the cost change is at the top. It's very easy to flip something like this around. Especially in a test, you're thinking of other things, and you know this is an easy question, so you want to do it quickly, and little mistakes happen. Change in y is 1,000 minus 750. Change in x, the number of items, is 50 minus 25. So then I get 250 over 25, a very nice 10. Nice. No need to worry about fractions this time, that feels good. I update my cost function. Let me know if I'm going too fast. Sometimes I feel like it gets a little boring because these are all familiar things, which is clearly the case. He's out of it. Too easy, too easy. So I don't want to do too many, I don't want to take too much time, but we do need to remember these things. 10x plus, I still need to find the b. So it's very similar to the question where we had 2 points. I now just use a piece of information, the first or the second one, maybe the second one, it's a little nicer, to find B. So I can say here also for $1,000, X is going to be 50, oops, not equal, and that's going to give me my B. B is going to be, well, that's 500, so 500. And so my cost function is y equals 10x plus 500. And I can then use that. They are asking for the cost prediction according to this function when I have 100 items. For 100 items, the cost should be, what do we get here? I'm plugging 100. 1,500? Oops, that's I mean 0. When I plug in 100 for x, set x equal to 100, then I have 1,000 plus 500, so 1,500. Straightforward, hopefully familiar, and if it's not, then some review may be required. It's totally up to you. You decide how much review you need. Let's do... Definitely want to do 4 and 5. Let's see, how much time do we have? Let's do 4 and 5, and then we'll see how much time we have. Number 4. Let's see if I have space here. So let's do number 4. I'm just making a new page to get ready. 4. The population of Canada in the year 1970 was 18 million, and in 1986 it was 26 million. Assuming the population growth is linear, write the function that gives a relationship between the time and the population, and use this equation to make some prediction. Okay, so let's write that down. What do we have? What do we have? So 1970, it was 18 million. 1986, it was 26 million. I want to know what is the function that describes population over time. So I have population size and I have time. Which one is the input and which one is the output? Gotta know, I need to know that. Input, output, which one is which? Which one is the time? Sorry, I didn't ask a nice question. Which one is the input? Time or population size? Time is the input. And population size changes because time changes. Okay. So let's step away from x and y. Let's say t for time. That represent. Now, when I work with dates and year values, it's not very efficient to let the time variable be the exact year number. You could, it's just not going to look very nice. And I don't necessarily care because I'm not interested in predicting the population of Canada in the year 1. There was no Canada. So it doesn't really matter that I have a full range of values. So often what works a little bit nicer is to represent the number of years, let's say from 1970. So 1970 would be t equal to 0. Because I'm only using it to predict the future. I don't really care about the actual 1970. That's often just making my function look a little nicer. So then here, for example, 1986 would correspond to t equal to 16, making the t values a little nicer. And what shall we use for the population? Let's use a p. Let that represent the population size. And I'm going to count that in millions. So I can then have just p equal to 18, p equal to 26. And the numbers are nice, 16, 18. They're sort of the same size. It's easier to work with in that case. But you don't have to, you don't have to do it this way. It's just for convenience. Then we've established that the population size is the output, so P equals MT plus B. And it's good now and then to just step away from the X and the Y. We're so conditioned to use X's and Y's, we almost don't think about them anymore. Changing the letters forces me to think which one's input, which one's output, what goes where. Just every now and then. So, I don't know, well, what do I know? Do I go to the slope first? It would work. But what would you want to do first? It's good to just take a few seconds and think. Maybe you see nothing? Maybe slope. Nothing wrong with that. I have 2 points. Why not? Sure. Let's go with the slope. I'll say something that I wanted to say later. So the slope, we'll still call it M. It is the change in what over change in what? What's the top one? There is no Y. That's the little practice challenge. And the bottom one is you can think of it, you can say to yourself X and Y, but there is no X and Y. Unless you define it, of course. And for practice sake, we change the letters a little bit. So I'm looking for the change in the population size, 26, or 18 to 26. So it's 26 minus 18. Change in time would be 16 minus 0. Or you get the same difference if you subtract the years, but technically that is not the t value. So I get 8 over 16, oh, very nice, 1/2. That's nice. Easy to work with. So I'll update to p equals 1/2 t plus b. What is the easiest, fastest way to find the b? Do I need to do anything, or are they giving it to me already? Because of my choice for my t input variable, the first point is when t equals 0, which is the y, quote-unquote, intercept, p-intercept in this case. So my choice has even more benefits that the b is already given as 18. So there is nothing to do. So my population function is p equals 1/2 t plus 18. If I chose it differently in how I define the variables, then I just have to plug it in and calculate b and so on. Not that that's incredibly difficult, just a little bit inconvenient. So there's my function. Then they ask if it grows according to this function past 1986, what does this function predict the population to be in 2025? So in the year 2025, in order for me to use that, I'm not going to plug in 2025 because of my choice of what the variables mean. I need to find the t value. So if t is 0 in 1970, what is the corresponding t value for 2025? 55. So I always have to go back and work with how the variables are defined. Sometimes that's done for me. Sometimes I have a choice, but you have to stick with that regardless. So then the p-value, I plug it in. Oops, no, plus 18. Decimal number is fine. What do I get? Half of 55, 27.5, plus 18. Can't do everything. You're like, sure you can. What do you get? Sorry? 45.5. Sorry, that looks like a colon. Okay, wait. So that means we write a little concluding sentence. Where's my? Stop erasing. There it is. There it is. In 2025, the function predicts 45.5 million people. Out of curiosity, what is the population right now? You have a phone? Just curious. How good is this prediction? Google knows everything, doesn't it? What is the population of Canada? 37. It's actually not bad. Not bad. Wow, it's surprising. Usually, when you get a linear function to use as a prediction, it has very limited use. You can't, oops, this is t. You can't look very far into the future. So for example, if I have t0 here, right? And what was the other one? 16. The population grew a little bit, giving me my straight line. But often past that, other things happen. It could go up, could maybe go down, and you can't look at that straight line too far from the points that you were given. So it's interesting. We're not that far off. Very nice. Any questions on this example? If you do it and you choose the actual year value, your answer would look a little different, but you'd still get 45.5 when you want to predict the population. Any thoughts? Yes?
When we update that p is equal to half of
Yeah.
a plus b, and b is given as 18.
Yeah.
What is coming?
It's based on how I chose my x variable, which is t in this case. I start counting from 1970, which means that my variable is 0 at 1970, which is exactly the quote-unquote y-intercept, which is the b. So I just plug it in. So I did that just for convenience. If you chose t to equal the actual year, 1970, you can't do that. You have to plug it in, and your b would look different, but you'd still get the same answer in the end. So it depends on how you chose your variables. Often, almost always, actually always. When I'm working with years, then I would count from a point to make the number nicer. And it has these added benefits of the b is already there and little things like that. But this is not the only way it would look. This is very much dependent on how I chose my variables. Good to remember these things. We have some time. Maybe squeeze in one more. maybe a number 5. So let me just make some space here. See if we can fit in number 5. I can at least get you started, and that's the most important part in case we run out of time. Number 5, and then tomorrow we will move on to something else. Let's go review. Number 5, the supply curve for a product is y equal to that. We'll write it down in a second. And the demand curve for the same product is something else. X is the price and y the number of items produced. Find the equilibrium price and number of items. Let's just write these down. So I have supply, y equals 1.5x plus 10. Demand, y, not 1, negative 2.5x plus 34. All right. So just in case you've never thought about supply and demand, this is often something where straight lines can be used very nicely. I'm going to do a very rough graph because we don't really need more. The supply is going to look something like that. Supply. The demand has a negative slope, which means it sits something like that. And the price settles down at what we call here the equilibrium price, where, oops, that was supposed to be U, where the supply and the demand match each other perfectly. So if I have the two functions, the two equations, the equilibrium point is where they intersect. How do I find the intersection of two lines? Yes. I set them equal to each other. So I'm going to zoom out a little bit so I can see them. So equilibrium is 1.5x plus 10 equal to negative 2. Is that a 5? X plus 34. Then I just have to solve for x here. I'll take the x's to the left, so that becomes 4x. And 10 to the other side, 24. So x is 6. And that is a point. So this x over here is a 6, but I also have the y value. How do I find the y value? I can plug it into any one of them, maybe the top one. So 6 times 1.5 plus 10. 1.5 times 6, that's 9. So 19. So 19. We're doing it very quickly because we're out of time. But still, I'll leave it up for a minute afterwards. So the equilibrium, let's write it again. Equilibrium price is, which one is the price? X is the price. 6, assuming it's dollars. And quantity is 19. So there's another kind of application, equilibrium between supply and demand. And often, it's not always straight lines, but surprisingly often, at least for a little bit, they follow linear functions and straight line equations.
Please remember to click the like button if you enjoyed the video, and to subscribe if you want to be notified of more videos. Thank you.